Hi everyone, welcome to our oral presentation on MultiBodySync, MultiBody Segmentation, and motion estimation via 3D scan synchronization. Consider a 3D dynamic scene with multiple moving rigid bodies. It could be an articulated object changing state, or simply several different moving instances. Suppose we are given multiple scans captured at different time steps. We aim at jointly analyze these inputs and simultaneously segment and register the scans. We start by considering 2 point clouds. As we see, each of the point clouds are consisted of 2 rigid bodies, the triangle and the rectangle, which are the things we wish to recover. First, we compute a low-level correspondence, estimated using a scene flow network. This correspondence can be fully explained by a permutation matrix, where the rows and columns refer to points in the source and the target. We use the flow vectors to estimate the local transformation with point at ++. Then, for each point in the source, we verify if the inverse of the transformation applied to the target point achieves the same effect as its backward flow vector. If so, this pair of points are likely to belong to the same rigid body. Doing this for all source points gives us a matrix, which we call motion segmentation matrix. The exact same procedure can be applied in 3D. We first compute the correspondence, and then compute the motion segmentation similarly. However, both these two may not be accurate. As we have access to multiple scans, we can exploit the cycle consistency between these scans to refine our results. The technique we are using here is called synchronization, which strives the coordination of events to operate a system in union. The idea has been widely used in timing, post-estimation, or language translation. In our case, we synchronize correspondences and segmentations. For correspondence, the intuition is that if point A is matched to point B and B is matched to C, then A and C are also likely to be matched. Given a graph where the vertices represent the scans and the edges are the inferred pairwise permutation matrices, for each node, we optimize for an absolute permutation, which matches the points in this node to a hypothetical universe space. We build an energy function to enforce the absolute permutation to satisfy the relative ones we've estimated on the edges. Additionally, we can introduce confidence scores for the edges. It turns out that optimizing this energy function is equivalent to solve an eigenproblem. The absolute permutations correspond to the smallest eigenvectors of the graph connection Laplacian matrix. This matrix is built by stacking the scaled pairwise permutation matrices. For the synchronization of motion segmentation, similar procedure can be applied as detailed in our paper. The synchronization operations are fully differentiable and can be easily integrated as a network layer using modern deep learning libraries. For our full pipeline, we first estimate all pairwise scene flows and confidences, and refine the flows using synchronization. Next, we estimate the pairwise motion segmentation matrices and synchronize to get absolute rigid body assignments. Finally, we can compute the rigid body poses for each segment using the flows and register them. Our pipeline is also iterable. The rigid body segmentation can help more accurate scene flow estimation and vice versa. This reciprocal process is demonstrated to improve the final metrics. Our method is evaluated on Sapien Articulated Object Dataset and DynLab MultiBody Dataset. DynLab is our new dataset with 8 scenes, 17 objects, and 64 dynamic configurations with fully annotated segmentations and transformations. We first demonstrate the effectiveness of our proposed synchronization algorithm. As shown in this example, direct flow estimation from the green point cloud to the orange point cloud gives bad warping results. The error is largely decreased with a full version of the proposed method and produces correct flows with the help of the other scans. Quantitatively, on Sapien dataset, our method outperforms all baseline methods in terms of both mean metrics and their standard deviations, reflecting multi-scan estimation consistency. Here are more visual results. Our rigid motion-based method produces consistent and robust results compared to the baselines. Notably, our method outputs decent segmentations on unseen RGBD sequences without the need of retraining or fine-tuning. In DynLab dataset, we reach robust multi-object matching and registration performance as shown here. We additionally compare to semantic segmentation and geometric clustering method and rank favorably among them. In summary, we presented MultiBodySync, a pipeline for segmenting and registering multiple dynamic scans with multiple rigid bodies. We incorporated weighted synchronization into a fully differentiable pipeline for generating consistent results. Future directions include improvement of scalability and robustness in more complicated dynamic settings. For more details, please visit our paper. Thank you very much.